Okay, so people are with us here. People attending virtually. Pardon me.
I think it's so cool being here.
Why?
Because normally I'm on there.
Oh, you're on the
Yeah.
other side. Oh, okay. Okay, so they can hear us. Okay, awesome. Great. So let's start just with the material that we need to know. So should we start with the ring part? The ring part is lighter. Yes. Normalizer and conjugacy classes. Okay, maybe should I do it now? I mean, I can explain at the end. Okay, just I'll finish the material, and then okay, so everybody can listen to me and everybody can hear me. Great, awesome. Okay. So first, I'll start with the material that needs for rings. Okay, definition of the rings and examples. Subrings. Definition and examples. 3 ideals. Definition and example. A very important theorem that ideals of Z are for and Z for some n. Then what we have? Definition of unit rings. Domain, integral domains. Okay. This is the definitions. This is the basics we have to know for rings. Okay. Great. Now so what the first two questions be? What do you want to? Okay. What are the first questions are going to be was the proofs that you're expected are just going to be from the following theorems. So for example, what's the first thing we prove? Let's proof for like product positions. So what's the first one? If 0R is equal to 1R, right? Then R is 0. That you have to know. Very fair question. Two. A field is an integral domain. Three. What did we do? What's the next one if you remember? Don't remember? Okay. A field is integral domain. Yeah, a commutative ring. Or let R be a commutative ring, or well, a commutative ring is a field. If and only if it has two ideals, right? 0R. This is a very important one. Okay. 2. Z mod and Z is an integral domain. I mean, some calculations you have to be asked. Things I can ask. Z mod and Z is an integral domain. If and only if n is equal to 0 or n is prime. Of course, here all rings from here on, rings are non-zero. And so all these definitions hold for non-zero rings. 1R is definitely zero. Okay, so you remember these are theorems that you can be asked to prove. Especially the bookwork part. You know, there's going to be a significant bookwork part. To upgrade bookwork means like from the notes. Okay, so there's going to be a significant notes part. These are very perfect questions. Okay, very simple, very quick. 10 marks. Should be able to get fairly easily. What is wrong? Okay, if you want me to go through one of these, I mean, you know, they're a bit long, so let's try not to. For a finite integral domain, is a field. This is also very important. Okay. This proof is very important. This proof is very important. Those proofs are very important. So it's a good idea to go through them again. Make sure that you know how to write them 4, 5, 6, 7, 8 times. Make sure you master them. Okay. Maybe I can do one of these if you guys want. Anybody in the online attendance want me to cover something from these proofs? Okay, great. Number 3. What's number 3? Okay. Maybe I'll just finish this everything and then try. Let R be a finite ring and every element, every non-zero element in R is either a zero divisor or a unit. Now this one I messed up in class. I proved something else. I didn't. But so if I were to prove it, I will give you the steps. I mean, I'll prove it now. Okay, I'll prove it now. I proved something else in class. I don't prove it. But okay. But I'll rewrite the whole thing. So, right. So if I were to put this, I'll give you all the steps. Okay, and then if you look at the lecture by lecture, I have it correct. Okay, for this one. I proved something else here, but the proof is not very different. Yes. Is either a zero divisor or a unit. Okay. So of course you have to know the definition of zero divisors and units, right? Okay. These are very important concepts. And you need to find the units of a ring, the zero divisor of C1 NZ, for example. We'll see this later on. Or with rings. Okay. So let me prove 5. So let A be different than 0R. So R is a finite coherent ring. Okay. Now, what is the function I consider in general to study type questions like that? What's the function I consider? X to AX. That's very good. So let F be defined from R to R. It's X to AX. You know this function X to AX, you gotta know it because it's used in many proofs, right? Right.
Just take it.
Yeah, exactly. It makes things work. Okay. It just makes things work because it has nice property. So if F is injective, if f is injective, since R is finite, then f is surjective. Right? This is the proof of phi.
Oh, sorry.
Proof. Okay. So if f is injective, since R is finite, then f is surjective, right? If you have a finite set and you have a function from R to R, if it's injective, then it's surjective. Then there exists x0 in R such that f of x0 is equal to 1R. So a x0 is equal to 1R. So a is a unit. Okay. Now, if f is not injective, what can you say? If f is not injective, then there exists x0, y0 in R. I mean, you can do it differently as well, but you can do it with the fact that f is a group homomorphism from R to itself. Okay, you can do it this way, but let's not do that. Let's stick to it. With x0 different than y0, such that f of x0 is equal to f of y0. This means that any x0 is equal to any y0, which means that any x0 minus y0 is equal to 0r. Now, since a is not a zero, since x0 minus, since a is different than 0, and x0 minus y0 is different than 0 by assumption, and a is a zero divisor. Okay, now I think in class I proved that it can be both at the same time. If it's a unit, then it's not a zero divisor. And if it's a zero divisor, then it's not a unit. Okay? It's exclusive. Like it can be a unit and zero divisor. Okay? X minus y is not equal to 0, and a is different than 0. So a is a zero divisor. Okay? Now it's clear that a and a unit and a zero divisor at the same time. Okay? Okay, I proved this in class, but that's obvious. Yes.
We have to show that it's well defined.
This is well defined, obviously. It is obviously well defined. You don't need to show it. Okay? There is no representative here, really. Yannick, Jan? Yeah. Yeah, Jan, so I will, this is what I'm doing now. I'll just tell you all the theorems you have to know. And these are, I'm starting with rings because it's a bit lighter than groups. And 2 of the questions are coming from the notes. Okay? Are we good here? Yeah? Are we good? Can you guys hear me? Okay, I think it needs some time to reach. Okay, great. Everybody can hear me now. Yeah, okay, thanks. Okay, great. So this is one proof that you can be asked. This is one proof that you can be asked. This is also important. And the ideal business that a commutative ring is a field if it has only 2 ideals is also important. Okay, so you can expect proofs like that. Okay. Great. I mean, these are short proofs in general. They're not very long. Great.
That ring's done.
Pardon me?
That ring's done.
No. Oh, still not done. We have a lot of them, right? We have like 15, 20 of them. I don't know how many we have. I mean, you should know them. Right? You should know them and know how to apply them. Okay, great. Now, ideals. The definition of an ideal, of course, you know the definition of an ideal. And you should know these very well. What you should know as well is following. So, shows that a set is an ideal, for example. So, if A is an R, then the set AR. So R is a commutative ring from now on, right? R is commutative. So AR, as R is an R, is an ideal containing A. That, for example, that ideal we use in the proof of R is a field if and only if it has only two ideals, right? This is the ideal that we use, if you remember. Yep. Did I give it a name? I just call it the ideal generated by A. I didn't give it a name. Well, I'll give it a name later. Yes. Tomorrow I'll give it a name. I'll call it the principal ideal generated by A. Okay? We've seen this before, though. Definitely seen this. When we prove that R is a commutative ring is a field if and only if it has only two ideals. In one way, when we do if it has only two ideals, well, if we assume it has only two ideals, we use this. Okay? Great. What else? Okay. And then importantly, the ideals of Z, for example, you should know what the ideals of Z are. And then we did an example also, ideals of R cross S, where R and S are commutative rings, right? You remember this? It's a product of two ideals. An ideal in R cross S is a product of two ideals. This is homework 9. These are very good examples that I can ask. I might ask things like that. Okay.
Is there such a thing as a cyclic ring?
Pardon me?
Is there such a thing as a cyclic ring?
Well, I mean, what do you mean cyclic ring?
We know there's a cyclic group.
Yeah, but cyclic with respect.
You tell me.
Yeah, so I mean, if you have a cyclic, if the additive group is cyclic, then yeah, you can. But then we don't say cyclic rings. It's just we don't say just cyclic. Okay. And the chat is connecting and disconnecting. I don't know why. Anyways. Okay, so these things like that are you have to be able to show this. Okay, these homework problems you have to be able to show that. Okay, great. Any questions on this? Great. Now we move on to homomorphisms. I think that's it for ideals. Okay, that's it for ideals. Then we're gonna move to ring homomorphisms. All of this. Ring homomorphisms. Okay, the definition of ring homomorphism. Yes.
So nothing on complex numbers.
No, there's going to be nothing on complex numbers. I didn't put anything on complex numbers unless it's z of I, right? Or c or the ring part, but I'll not ask you multiply like I complex numbers. But yeah, I won't ask you. Okay, so the definition for ring homomorphism. What is the definition? It's a group homomorphism. Phi of 1 must go to 1, and phi of x1 must be equal to phi of x, phi of y, right? Okay. This we have to know. 2. Prove that there is no ring homomorphism. Rings that also we have to know. Okay, if I give you 2 rings and I tell you there is no homomorphism, you have to know how to do it. This is like homework 9, right? Homework 9, we had plenty of examples. Okay, and show sometimes show that there exists a ring homomorphism. I find you more into ring homomorphism, also homework 9. Okay. We did it from z mod nz to z mod mz when m divides n, right? And then we did it from z4 to z2 cross z2, if I remember, like things like that. Okay, you should be able to do that. I'll give more examples of these calculation questions. So these examples could be very, very nice calculation questions. Okay. Pardon me?
What are that?
Yeah, I mean 2, 3, yeah. 2, 3 could be nice calculation question. Okay, great. Now, okay, I mean, so homework 9 is homework 9. Nice calculation questions. Yeah, of course, these are not the only possibilities, but homework 9 contains very, very nice calculation questions. Okay, so you could see something like that in your final. Okay, so for example, show that q root p is not isomorphic to q root q if p and q are distinct primes, for example. Show that there is no homomorphism from z of I to z mod 7z, things like that. Okay, things like that you can expect in small calculations, and okay. I'm not saying it's going to be that, but you can expect things like that. Okay. I mean, we still have like polynomials. They will also be very fit in calculations as well. Finite fields and things like that. Yeah. Characteristic could be good for proofs or calculations as well. Yeah. Okay. So that's so this is homework 9 has nice calculation questions. Again, it might not be the exact same question, but I might twist it a little bit, might change things a bit, spice things up a bit, things like that. So homework 9 is very good to understand rings. I'll post more practice problems on polynomials. We'll cover these on tomorrow and on Friday. So I'll post practice questions. They're also very nice calculation questions. Okay, great. Now, what as well? Yeah. So kernel of a homomorphism is an ideal. Kernel for ring homomorphism is an ideal. Ring homomorphism is injective. Right from R to S. Injective. Only if what the kernel is 0 R. Now, if I ask you to just prove this, prove that the kernel of a homomorphism is in the homomorphism, a ring homomorphism is injective if and only if the kernel is 0. You cannot just say I know this from groups. Okay? You can prove the one for groups and say, okay, this is true. Or you can just prove this one. Okay? So you have to use your judgment on things. So for example, say I tell you prove that a group homomorphism if and only if the kernel is the identity. A group homomorphism is injective if and only if the kernel is the identity. And then the next step, prove that the ring homomorphism is injective if and only if the kernel is 0R. Then here you can say use the previous part. But if I tell you just prove this, you either have to show it properly or show it for groups and then apply it. Okay?
In class, we didn't show
Yeah, but you can the same proof will work, right? So if phi of x is equal to phi of y, so assume that the kernel is 0. If phi of x is equal to phi of y, then phi of x minus phi of y is 0s, right? This phi of x minus y is 0s, so x minus y belongs to the kernel of phi, which is assumed to be 0, so x will be equal to same way. Same way you do it for groups, you can prove it, or you can prove it for groups in general and do it for x. Okay? Great. But you know, if I ask to show it for groups, you cannot do it for rings and then show it for okay? Yeah.
Is there anything additional you need to say for groups? Can you just say it's been proved for groups that
Because every homomorphism
yeah,
group.
and then you just say
Exactly. Yeah. Let's see, there are questions, a lot of questions being asked. You mentioned homework now. Are there going to be any questions? I mean, I think I've answered that many times that you might see questions from the homework as is or a bit twisted, right? I said this, no? Yeah. I said this, right? You can expect questions from the homework as they are, or a bit twisted, or yeah. Yep. Most important 7, 8, 9 are the most important ones, but that doesn't exclude 6, for example. Or 5, or any like it doesn't exclude them. Okay, you should be able to know everything. But again, the focus is going to be on the post midterm part. So I'd say the more important ones are 7, 8, 9. Now I didn't check every single question. What homework is it in, or I didn't check that. But in general, like the later ones, group actions are very important.
there are some.
Yeah, exactly. Unless it's the question. Unless it's the question. Okay. Unless it's the question. You can say I proved in the homework or this is a class theorem. Okay, so this is it for rings. This is it for ideals. Now I have properties of homomorphisms, properties of group homomorphisms, of ring homomorphisms. I wrote the homomorphisms. You know that phi inverse of an ideal is an ideal, and the phi inverse of and if phi is surjective, then the image of an ideal is an ideal. Things like that. I think I wrote them all down. So that I wrote them in the notes. So you have to know them. I don't think I'll ask you to prove them. I don't remember that I asked you to prove these because I didn't prove them in class, but it's a good exercise to do. And then ring isomorphism. Really, I mean, basically 2 rings are isomorphic if you have a bijective ring homomorphisms between them. And then you can say R is if R is isomorphic to S, R is a field if and only if S is a field, and things like that. So whatever holds for R when it comes to its ring structures holds also for S when it comes to its ring structure. Okay, so things like that. These could be nice calculation questions. Use these. Maybe you would have to use these and not prove these. For example, if I tell you is Z mod I don't know. Let's say I give you a field, for example, a field with 25 elements, and I tell you is it isomorphic to Z mod 25? No, because Z mod 25 is not a field, but the field that you gave me has 25 elements. These two are not isomorphic. You didn't really see a field with 25 elements. But let's suppose I give you a ring with 25 elements that is a field, and I tell you is it isomorphic to Z25? Is Z25 a field? Z mod 25Z a field? No, because 5 times 5 is equal to, in that ring is equal to what? Yeah, 5 times 5 is 25, which is equal to 0. So this ring has 0 divisors, so it's not an integral domain, so it's not a field. Okay? Great. Questions? Great. And R is a domain, R is an integral domain. And F is an integral domain. And things like that. Okay. Great. Now there's one more important thing, or one important things. I is an ideal, then I is the kernel. Of course, I'm working with R is a commutative ring. Always R is commutative and non-zero. Okay, so if I is an ideal, then I is the kernel of a homomorphism, of a ring homomorphism. What is that? What is the ring homomorphism? It's from I to the set of cosets R mod I that sends R plus I. I mean, of course, you have to know R mod I. The quotient group or the quotient ring R mod I, you can see that's a group where you have a well-defined operation, well-defined addition and well-defined multiplication of it. Okay, so you have to also know the quotient rings. Okay, all good here. So this is so far. I mean, okay, that's still a lot of stuff. There's still 2 big parts, but this is the stuff I expect from you, at least in some of these questions. Okay, great. Quotient rings, I mean, you know, just congruence relation mod I, you know, congruence mod I. We've seen these congruence mod I. If A is congruent to B mod I and C is congruent to D mod I, then AC is congruent to BD and A plus C is congruent to B plus D, right? You remember these? This is how we showed that the operations on R mod I are indeed well-defined operations and turn R mod I into a ring. Okay, so these you have to be able, I will not ask you to show that the operation is well-defined because it's a more or less not very interesting question to ask, but you can have to use it. You can have to use the congruence property mod I, okay, in some questions, especially the calculation type questions, okay? Great. Yeah.
You know how you're saying like there's like several methods to answer like certain questions?
Yep.
Would there be questions where there's like really only one clear method or no?
I don't know. I don't know. You can find some only one. It may be only I know that I only know one. Maybe some of you will come up with another better way of answering, or yeah. So it's not a. I don't know. You know, I don't like look at all the ways of solving a question. But if you solve it and you solve it correctly, even if it's not the usual way, especially if it's a proofing class, you do it your own way and you have it correct and it's complete, then yeah. Okay. Great. Any questions from people attending online? Any questions from people attending here? Let's wait for the people online. I think it takes like 20 seconds to reach them. Here, any questions on this? No questions? Great. Now, what's the next important part? Oops. No, all good. Thank you, Miriam. Okay, no questions? Okay, now we move on to the next important part. What's the next important part? Characteristic, right? And rings. Exactly. We're doing rings now. characteristics. Does this help? Does this like help you at least like restrict the range by like 5% of things you have to know? I mean, it's still a lot, but you know. You know, the next important part we've seen in rings is the characteristic proof. Okay, I mean, you're going to have a question on the characteristic of the ring. It's not something that I'm not hiding that you're going to have a question from here, be it a proof or a calculation. You will have a question from here. Okay, so I'm not. Okay. Great. So how do we start? What's the definition? I mean, you have to know the definition. So first of all, if R is a ring, of course, R is a non-zero ring. Okay, always R is assumed to be non-zero. Okay, if R is a ring, and there exists a unique ring homomorphism. What did I call in class? I called it 5, right? 5 from Z to R. Oops, R is not a R. And what is phi of n? Phi of n is this one. Is n times 1R, which is defined to be this way. I don't know if I wrote this. It's the sine of n times 1R plus 1R absolute value times, right? Did I write it this way? I just wrote it, if n is positive, it's 1 plus 1 plus 1 n times. Okay. It's 0R if n is 0, and it's minus 1R plus 1R n is negative. This is absolute value of n times. Okay. So which is minus n of x. Okay, so it sends, you kind of define the 2 in a ring. What is 2 in a ring? It's just 1 plus 1. Okay, now I won't ask you to show us a homomorphism. It's tedious. It's not very nice. And I won't ask, I mean, I could ask to show it's unique, but I won't do it. Okay, you just have to know the same. I mean, uniqueness follows just because it's a group homomorphism and it's a ring homomorphism. So any group homomorphism that send the generator to the same thing are equal on a cyclic group because that is cyclic group. Okay. Any questions here, guys, on the online? Yeah, just I'll wait. Yeah.
You see, like, right, that sort of thing in tech that was saying, write out as like sine of n minus 1, k.
What? No, this is sign of a transpose of a permutation. That's not a yeah, sign of n. This is just the sign of a number. It's if this number is positive, sign of 5, for example, is 1. Sign of minus 1 is minus 1. Sign of 0 is 0. Okay, have you seen this notation before? Sine of x. I mean, many people define it different ways, but if x is 0, it's 1. Okay. Great. The k I defined for permutations. Yeah, this is a number. Sign of a number. What's the sign of 5? Positive or negative? Yeah, no, it's not permutation. Just a number. Sign of. What do you mean? Yeah, sign of a number. The other is a sign of a permutation. That sign of a number. But I mean, if you don't like the notation, just use this one. Okay. Yeah.
I think we have to know sign.
Yeah, the sign of permutation is something that you should know. Yeah. I'll go through this again. And this is just let's release that. Let's pretend that we don't write it. Let's write this one here. Okay. Great. Okay, this is a homomorphism. This is the unique homomorphism from Z to any ring R. Okay, great. Now, what's the kernel of the homomorphism? Oh man, okay. Kernel of phi is equal to nz for some n. And for some n bigger or equal to 2, or n is 0, right? This is the kernel of phi. And what do I define the n such n is unique? N is called the characteristic of phi. Okay, this is how I define the characteristic. Right? You remember this? Okay, so it's good to know that. 2. Now, let R be a ring, let n be bigger or equal to 2. R has characteristic n if and only if one R had additive order n. That's a very important theorem. Okay, I proved it 2 ways. If R has characteristic n, R has characteristic n if and only if the additive order of 1 n R, let's say, so the order of R and R with respect to addition, okay, as additive order n. Okay, this is a very important theorem. You should be able to. Okay, in both ways. Yes, it's not very long, but Okay, any questions on this one? Yeah.
Can you explain again like why n equals to 1?
Oh, because why can't n be equal to 1? So if n is equal to 1, this means that everything is in the kernel, right? Now, I assume that 1 will go to 1, so not everything is in the kernel. 1 and z, where will 1 and z go to? It will go to 1r. Okay, and 1r is different than 1z. Phi of 1r
Okay, so you got
is 1r different than 0. So 1 doesn't belong. Okay, so curve phi is not everything. Okay, great. So this is when it comes to characteristic. This is the first theorem you have to know, and then you have to show examples. For example, things characteristic of z, vz cross z2z, the product ring. What's the characteristic of this? Is the additive order of the multiplicative identity. What's the multiplicative identity in here? This is 1 mod 3 and 1 mod 2. Right? What's the order of this one? It's the LCM of 3 and 2, which is 6, right? Yeah, that's characteristic 6, right? That's 6. Okay, what's the characteristic of Z4 cross Z2? What's the multiplicative identity of this one? 1, 1, right? What's the multiplicative identity of this ring? 1, 1. What's the order of 1, 1 in the additive group Z4 cross Z2? LCM 4, 2, which is 4. Yeah, very good. It is 4. Okay. Characteristic of Z mod 7. What is that? Z mod 7 is. Okay. Are we good here? Is that clear? So questions like that could be very, very nice computational question. Find the characteristic of this one. I test your knowledge on the group order. And it's gonna be, and how do you find the order of an element in a group? And then you can just apply the definition of this characteristic. Yeah.
Would we get 4 marks just for that?
Yeah, you should justify it, of course.
Oh, because we got a grade of homework 6 and it just said write down, name all the subgroups of something somethings, and I just wrote them down.
Yeah, no, I mean you have to justify. Even if I tell you write down, you have to justify. Unless I tell you, don't justify. Okay. So okay. So things like that. These are good examples. Now, there's another theorem. What's in it? Yes. What's the order of 1 here? Is LCM of the order of 1 here and the order of 1 here, right? What's the order of 1 here? 3. What's the order of 1 here? 2. What's the order? What's LCM of 3, 2? Yeah.
You won't ask us to prove the LCM.
No, unless maybe the question before would be like prove that. Yeah, that's before I tell you. So if little g and g has order n and little h and h has order m, prove that the pair g h and g cross h has order LCM of n. That's a very valid proof. Yeah, that's in the homework, right? Prove this in the homework. Yeah. Yeah.
So if you're just trying to be sure, we say that it is LCM
Exactly.
each group, and then we say like
LCM
is
6.
That's enough.
Yeah. So the characteristic is 6. Exactly. Unless I tell you show it as order 6, so you have to do it immediately, for example. Okay? Unless I tell you show the calculations that we do. I will make it clear if I need to do that. Okay. Okay, any questions? Great. Now what's the most important what's an important theorem here? Another one. R has characteristic 0. And only if 1R does not have finite order and R, right? I didn't prove this theorem. I left it as an exercise, but still could be there. Right? I did this theorem, right? I did this one. Yeah. Great. Yeah.
Prove it that.
Do you want me to prove it? No, I think I did prove it. Did I prove it or not? No, I did prove it. I did prove it. I did prove it. Yeah, I did prove it because I remember I proved it. No, so it's something else that I did yesterday. That I remember. Yeah, yeah. Monday. I mean, these are short proofs that. This.
know how to do it.
I mean, yeah, you should. I mean, these could be calculation questions, right? So like. Yeah, I don't know. I mean, it's something that's very theoretical. Okay. It's yeah. 1 plus 1. Yeah, it could be a number, for example. Let f be a field where 1 plus 1 is 0, for example. Show that f has size 2 to the m for some m and n, for example. Okay. Instead of b, I give you a value. Okay. All like many questions will contain numbers. Numbers won't be relevant, I think. And most of them, except in one or two questions, numbers will not be very relevant. I think. Anyways, that's not a. Oh, we'll see. Can't remember what I put it there. Okay, things like that. What is what? What's an important theorem? Let R be a ring of characteristic n. Let R be a ring of characteristic n. Then what can I say? Then the order. Then any x in R as additive order dividing n. Right, so it has finite additive order. Of course, it will be finite here. You remember this proof? I just showed that x plus x n times is equal to 0 by just factoring an x out. So I say x plus x n times is x times 1 plus 1 plus 1 n times, which is equal to x times 0, which is 0. Perfect question. This is a perfect type of questions. 2, 3 lines. Boom. Yeah.
Wait, what do you mean then every x is R?
Every x in R. So this is in R. Then any x in R, thank you, has finite additive order dividing n. Okay. I did this in class, right? Yeah. Now, this is another important theorem. If R is a ring, R is a finite ring of prime characteristic, so the characteristic is prime, P, then the size of R is P to the M for some M and M. If you remember how I showed this, it's by Cauchy's theorem, right? You show that any, if you have any Q dividing the size of R, then that Q you must have an element. So, I mean, you should use the previous proposition. So any element must have order dividing P, right? Now, any non-identity element will have order P because P is prime. And then if you have another prime dividing the size of R by Cauchy's theorem, so say you have a prime Q dividing the size of R, by Cauchy's theorem, you have an element of order Q. So Q must be equal to P. So P will be the only prime dividing R. And then since R contains two elements, then R must be of the form P to the M, where M is strictly bigger than 0. Okay? We did this in class. Definitely we did this. This is a very important theorem. So please revisit the proof. Next term, as I said, you will do it in a better way. Just say it's a vector space over Z mod PZ, for example. Okay? Is that clear? This we did in class. Okay, so these two questions, part 1, part 2, would be perfect together. Okay? So A, let R be a ring of characteristic n, then show that any x in R has additive order dividing n. Part 2, if R is finite and has characteristic P, where P is a prime number, show that R has size P to the n. This is a perfect question. Okay? Yeah. Exactly. It's M is not 0, so otherwise R would have size 1. But R has at least size 2 because R has two elements, 0 and 1. Exactly. Okay. So these two together would be a perfect combination of questions. Great. Now what else? And then, for example, I can give you, find a counterexample to this, that R does not have prime characteristic, and R doesn't have size P to the M, and R is finite. For example, Z4 cross Z2, what's the characteristic of Z4 cross Z2? 4, right? Does it have size 4 to some power? No. It has size 8. So this is a counterexample if P is not prime. For example.
2 is prime.
No, the characteristic is 4.
Oh, the characteristic has to be 1.
Yeah, exactly. So that this works. Exactly. Okay. Great. Now, another important one. Let F be a field. Then F. Let F be a finite field, I think. I said let F be a finite field. Then F has characteristic P or some prime P, right? I proved this in class. I mean, I think in class I said then curve phi is equal to PZ from some. Yeah, but that's the same, right? You remember this from class? No? Yes? So I proved that, or I can formulate the question many ways. I can say show that curve phi is equal to PZ for some prime P. Okay? Things like that. These are very cute questions. Could be proofs, 2, 3 lines. You have many of these, so you have to study them all. Okay. People attending online, questions? People attending online. Nope. Okay, so these are very, very nice questions. So it's you can expect that one of these is there, or calculation wise, or but you will have a question on characteristic. Well, we have 2, 3 more questions that we could add, we could talk about. Okay, is it clear? Is it yes?
Just like this is the same thing. And should prove
PZ. Yeah, exactly. No, class I wrote pure phi is equal to PZ for some P. I didn't say it has characteristic P, but it's the same. The question is the same. I can tell you, show that F has characteristic P, or show that the kernel of phi is PZ for some prime.
So like all fields have like
All finite fields have prime characteristic P. It's not the same prime. So
Yeah.
take Z mod 2, for example. What's the characteristic of Z mod 2? What's the characteristic? It's a field, right? What's the characteristic of Z mod 5? 5. What's the additive order of 1 in Z mod 5? How many times do you need to add? Okay, we'll see more fields. So all finite fields have prime characteristic. Another important theorem we proved last time: if F is a finite field, and F has size P to the M or some prime P and M in N. So if F is a finite field, then the characteristic of S is prime, right, by this theorem. And by this theorem, since F is a finite ring, then this one goes, right? What as well? We proved that the characteristic of an integral domain is either 0 or a prime. I left it as an exercise, right? You should try it. It's a very good exercise. It's a very, very good exercise. So if R is an integral domain has characteristic 0 or a prime number. Okay, so can you have an integral domain of characteristic 4? No. Okay. Great. I think this is it for characteristic. Did we? This is it, I think. Yes. I don't think we have any more things on characteristic. Yeah, so it's 1 hour, I think, of ring materials, plus the theorems we will cover. Like plus integral domain, yeah. So plus the stuff we will do tomorrow and Friday, and the examples will continue. Okay. Does that help? I mean, it's still a lot of stuff, but this is what you can expect for some of the questions. And then, I think I put one more. So if you have a ring of characteristic n, then Z mod n is a subring, is isomorphic to a subring of this ring. But this is object. Okay. I wrote that. Did I write that yesterday? If R is a ring of characteristic n, then Z mod nz is isomorphic to a subring of R. Yeah. So that's all. Yeah. Visual picture?
Yeah.
So 1 plus 1 plus 1 plus 1 n times. So take the cyclic subgroup generated by 1. 1 plus 1, 1 plus 1 plus 1. And then you stop at the characteristic. This is really Z mod nz, right? That's it.
We didn't prove them.
We didn't prove them, no. You want to prove them? I mean, it's did you try them or not? Yeah, okay, so try them. They should be very, very quick if you know the proofs of all of these. They can be very quick. I mean, I can tell you how to do that. So Z mod curve phi would be a subring of an integral domain, right? Now the subring of an integral domain is an integral domain, right? So curve phi is either 0 or pz. That's the proof. Someone raised their hand. Yeah.
Oh, sorry. Did you just say that since it's an integral domain, it's a field, and then
No, because it's not necessarily a field. A field is an integral domain. Z is an integral domain, but not a field. Okay? Okay? A finite integral domain is a field. Now, in this case, you use it, I think here, you use it, right? So if F is a finite field, then you say that Z mod curve phi is isomorphic to a subring of F. So Z mod curve phi is a finite integral domain, and Z mod curve phi is a field, because a finite integral domain is a field. Yes. This is the one you're trying to mimic.
yeah.
Yeah, exactly. Here you're using that the integral domain is finite. Okay. Great. So please know these proofs. You should know them by heart. You know, like you know your name. You should know these proofs. And again, if you know it, it's very quick. 5 minutes, you're done the problem. If you don't know it, then good luck. You know, you might not be able to come up with it. Okay, so know the proofs, rewrite them. Just rewrite them. Rewrite them. It's gonna take you maybe 5 to 10 hours to just rewrite these, and another 5 to 10 hours to master these. So it's gonna take you 10 to 20 hours to master this chapter at most. At most. It's the same trick over and over again. So once you memorize the trick, you take Z mod curve phi, you see what that is. Okay, this is the same trick over and over again. So once you memorize the trick, once you memorize the way to do it, then it's gonna be fast. Okay, so this chapter should take you maybe not more than 20 hours at most. At most, right? Why did you? How long did it take you?
No, it just says 20 hours, like something.
Yeah, no, I mean it's I know. I mean you still have like 10 days, 15 days. But I mean, you know, oh no, not 10 days. No way. 10 days, yeah, 10 days.
Was that for ring or just for characteristic?
No, I mean for the entire rings, I think it should take you. The other stuff this is the hardest part of rings, right? Yeah, this is the harder part of rings. The characteristic part. So I mean, you know, 20 hours, no, 20 hours is exaggerated. 10 hours should be fine. Okay? 10 hours to study this chapter, to master it completely, to know every single truth, every single detail. 10 to 15 hours should be fine. At most. Really at most. Okay? I mean it's I think you should put maybe like 3-4 days of study to this, right? So maybe 10 hours every day, something like that. Yeah. I know, but every class takes that much to study for, you know? Every math class takes.
So we don't have like
Yeah, but math classes take that much time. They you're gonna prepare well and be have 100 of it. I was a math student. You're gonna prepare well. You need to know every single proof, especially if it's proof writing. If you have to do the bookwork part of the notes, then you have to take that. Even like maybe I would say if you master the things very well, 2 hours should be enough. Honestly, if you master the thing very well, try to master the things very well. Manage to reduce it from frantically to. Yeah, exactly. I mean, you know, but that's I mean, that's how exams works, right? You need to have complete mastery of it. The midterm, how long did it take you to study? How long? Very long. Way too much, but at the end it paid off, right? Peter.
in the final.
Way
More times.
Yeah,
Like
exactly.
even 100 more times than the midterm.
I don't think it's 100 more times. If you worked through the terms, it's going to be quicker. Okay, so if you work through the terms, it's going to be quicker. Then so it's going to be. I mean, now the midterm content feels easier, right? So it's and again, the bigger part is going to be post midterm. So you might have a question on pre-midterm part. So, if you need to choose, a situation, if you need to choose what to study, let's go for the post-midterm part. Okay. It's gonna be fine if you study it. Okay. If you don't study, then it's yeah.
Did you say it before, like, there's not gonna be like a direct proof of-
Before the midterm, there is not going to be a direct proof. Right? Okay, so all the proofs are going to be from the post midterm part, and I think I eliminated a few proofs. Like, I'm not going to ask you prove the first isomorphism theorem. I'm not going to ask you that. You have to use it, but I'm not going to ask you that. Pardon me?
I know.
Sylow 2 and 3 are fair game, yeah. But I mean, you've done these, right? You've done Sylow 2 in a homework. You've done a version of it in a homework. You've done Sylow 3, well, I don't think so. But you should know the key parts. But then, I mean, it is what it is. This is the math part. You should study really a lot. Unfortunately, or fortunately. But the midterm usually ended up well for, I mean, the average is 74 and the median is very high. So midterm, if you studied a lot, then you just have to probably repeat the same thing here. Okay, don't. When is your next exam? Third?
You have 2 midterms on your third.
Oh, okay. When is your next final exam? When is the next final? Like this final is the first. When is the final after?
16.
Exactly. Pardon me? Algebra. Algebra and something else. Math. Oh, geez. Okay. Yeah. These are very demanding things. These are very demanding because you need to know all of these differential equations. That is a very demanding. But what can I do? I don't set up the final schedule. Okay, so please just study this. It's gonna take you a while, but once you master the key ideas, boom. Yeah. Oh, definitely. I mean, definitely, yeah. Definitely. But I think homework 7, 8, 9, homeworks 8, 9, I graded them all. So it's there's a reason why I graded them all because they're important. Okay. 8, 9 are all graded. I think, except 8, 5 is not graded. The last question is not graded, but I put it on the next homework. So it's okay, great. So these, and then you have to know the Chinese remainder theorem. If it helps you, I'm not gonna cover it. It's one less proof. Okay, if it helps. But it's a one-liner, so it's not gonna be a big deal.
Oh, so it's not need a.
No, Chinese remainder theorem I won't ask you. Yeah. Okay, so any question? Yeah, so Jason, yeah, no proofs from pre-midterm. No proofs from pre-midterm. Okay, great. Are we good here? Okay. Are you guys okay with this? Any questions on that? So this is what you should know for rings. Now, everything polynomials will be in calculations. Okay, I'll be very clear what to expect. Polynomial rings. We'll go into calculations. Okay, I might mix polynomials and characteristic and things like that. Okay, I mean, we will cover these on tomorrow and Friday. Fairly simple, I think. I'm not gonna ask you a tough question. Maybe just to check that you were present, give you like 20 practice questions just to make sure that you have it, that your muscle memory is there, and then you probably just have to reproduce some questions of the question. Okay. Okay, great. So this is it for rings. Again, instead of like just trying to memorize the proofs, first write them, get the idea behind it, and then try to repeat the idea many times. Okay, you see, it's the same idea. I mean, did anyone study this chapter? You studied it? You see, it's the same idea repeated every time. Same idea, same idea. Get used to the idea. The first isomorphism theorem. Subring of an integral domain is an integral domain. Subring of a finite field is a finite integral domain, hence is a field. Things like that. Okay. So, like the midterm was in general well succeeded because you studied. Okay. In general, it was well succeeded, and because you studied well. Yeah. Any questions? Yeah.
Like, would you say it's better? Was obviously better to like understand all these concepts conceptually. But let's say you like can't wrap your head around it, just like learn it by heart, like whatever. Like, even if you learn that thing by heart, you don't know how to apply it.
Yeah, I'm not saying. Because if you learn it by heart, I can tell you yes. But if I switch it by like one word, then you will be lost. Right? This is the problem. If I tell you yes, learn it by heart. Just learn it by heart. Now, it's a good idea to learn them by heart if you understand them. Why is that? Because say you forgot something, you can try to, in the exam, you can try to work your way through it if you understand it. Whereas if you just memorized it and you don't understand what's happening, say you had a blank, for example, during the exam and you just forgot, or you panicked a bit and you forgot, or I switched the question a bit and you forgot. What do? If you do not understand, then it's more difficult to, rewrite it. Yeah. Yeah, but you might not know that this is the question. For example, if I tell you show that the kernel of phi is the ideal pz for some prime p, I wrote it this way in class, right? But if I tell you show that f has characteristic b, then you would look at it, you were like, I don't remember that question. Exactly. No, I'm just saying, like, if you don't know the definitions, you will just be, you might not be able to get it. So it's better to understand. And again, I'm not here to trick you. I'm here to help you. Class recording be posted. We won't be asked to prove the Chinese remainder theorem. No, we won't be asked to prove it, although the proof is one line. The order of Zn cross Zm, the order of 1 in Zn cross Zm is LCM Mn, which is Mn if Mn are co-prime. Yeah, so, okay. Both cases. Okay, if that one less proof, I won't ask you that. Okay, great. Any questions on the ring part? This is the ring part. This is what you have to know for the ring part. I could go maybe now for the group part. It's going to be a bit faster because I need to finish it up. But ring part, this is what you have to know, especially for the proofs. And if it helps you more, I don't know. Polynomials are going to be covered in calculations. And the two proof questions are going to come from here. Okay? Doesn't help much, but now you know what to expect. Okay? Great. Now the group part is going to be way harder because we covered way harder stuff in groups. So what is the thing to focus on? Orbit stabilizers, homomorphisms, group actions, coset representation. Key groups. Groups are very important. Sylow theorems. Yeah, Sylow theorems is all P groups, right? So yeah, Sylow theorem is P groups, so it's covered in Sylow theorems. Great. Okay, so which one do you want? Do you want to start in order? Group homomorphisms. Okay. Group homomorphisms. I mean, I went the homomorphisms. So I recognize the definition and basic properties. These could be a nice proof. These proof questions. Prove that phi of G inverse is phi of G inverse. Prove that phi of EG is EH, right? These could be nice proofs. If phi from G to H is a group homomorphism, then the identity goes to the identity. and G inverse go to phi of G inverse. Yeah. Things like that could be nice proofs. Definition and basic properties. Kernel phi. What is the kernel of phi? So ker of phi is from G to H, right? Kernel of phi is just the set what we call X and G or G and G, such that phi of G is equal to EH. So what are the properties of the kernel? Kernel is a subgroup. Per phi, the subgroup of G. What else? No, very good. That's it. Is a normal subgroup of G. And what as well? What's another very important property? EG. If and only if the kernel is equal to EG. Exactly. Very good. These are very good. See? Is it bad? It's not that bad. You studied groups, I guess.
Yeah.
Why is injective? If and only if kernel phi is EG. Very good. Yeah. Mhm. Yeah. Isomorphic to identity. Yeah.
G only has one element.
Yeah.
But like when you like it's multiplying two things, I don't get how you multiply two things and there's only one thing.
G mod EG. So how many cosets does G have in itself? Only one, right? Which is the identity times G. Okay. See it this way. Okay. Yep. For groups, yeah, I'll just reach it now. Okay, I'll just reach it. Okay, so these are very three basic properties of the kernel, and I can ask you, direct questions on this. For example, so show no surjective homomorphism. Well, this is the first isomorphism theorem reading, but anyways, from S3. Let's say to Z mod 3. Okay. So if you have a surjective homomorphism from S3 to Z mod 3, then you need to have a kernel of size 2, right? And then you know that S3 has no normal subgroups of size 2. Okay, that you can, things like that, very short. These are good questions that I could ask. Of course, things will be a bit harder, like you will get harder questions. Okay, but this is a cool question that I could ask. About no Cauchy's theorem proof, I won't ask you about that. You'd have to know it, but I won't ask you about Cauchy's theorem. I won't ask you about the proof of Cauchy's theorem, but you have to know the statement, yes. But no surjective homomorphism, for example, that's an example. Maybe I should write the first isomorphism theorem. G modulo kernel of phi is isomorphic to phi of G, right? For groups. And then isomorphisms of groups. I mean, this is really isomorphism groups. Showing that two or more groups are not isomorphic. Right, so groups of order 6, I can tell you show that S3 and Z6 are not isomorphic. Or groups of order, let's say, I don't know, 8. Give me 5 groups of order 8 that are not isomorphic. Things like that. Okay? Great. example. This is an example. This is not the only way, but this is what you can expect. Yeah.
Sorry, back of the, I just realized that by phi equals G and G, that phi G equals phi.
No, 5G is equal to H, the identity in H. Yeah. Okay, so things like that you can expect from groups. Okay? Things like the homework. Give me 5 non-isomorphic group of order 8, Z2 cross Z2 cross Z2, Z2 cross Z4, Z8, D4, Q8. Okay? So you had a question on the first isomorphism theorem. Yeah.
It's only one. And the one is injected.
5 bars injected. 5 bar with the quotient group to phi of G. Yeah, it's injective. I showed that the kernel of phi bar is the coset curve phi. Curve phi bar is of G mod curve phi. It's the coset of curve phi. It's the coset curve phi. So the kernel of phi bar is the identity of G mod curve phi. Agreed? Yes? What's the identity of G mod n if n is normal? This perimeter part. That's the coset n, right? So what's the coset G mod curve phi? What's the identity coset? Curve phi, right? So I showed that the kernel is exactly the coset curve phi. Now look at the previous one. Phi is injective if and only if curve phi is the identity. So what's the kernel of this phi bar? Is the identity of G mod curve phi. So it's injective. Is it clear? You can work it out directly as well. Okay, but I wanted to use that theorem. Okay, is it 100%? Is it good? Okay, great. So I won't ask you for the proof of the first isomorphism theorem. I won't ask you for that. Okay, it's more interesting for me to ask you to apply it.
Could you do that example of show notes?
Yeah, sure. Do you want me to do it in detail? In detail? Okay, yeah, sure. If phi from S3 to Z3 it is rejected. Group homomorphism, then curve phi has size 2, right? Because 6 G mod curve phi would have the same order as Z3. S3 has size 6. 6 divided by curve phi is equal to 3, so curve phi would have size 2. Right or no? Yeah. So S3 has no normal subgroups of order 2. Right? Yeah, all the subgroups of order 2 are 1, 1, 2, 1, 1, 3, and 1, 2, 3. None of them is normal. You see that?
Yeah.
Okay. Okay, so this is for isomorphism of groups. Still have a bit of time. Okay, read this is for the first part. Now, the most important part is group actions. Okay, this is going to be more than a third of your exam. Okay, I'd say like 30 on 70, something like that, are in group actions. Almost 3 questions maybe on group actions. Okay, you can solve with group actions maybe almost 3 questions out of 5.
But I just don't understand, like, how does it work, like, to just solve with the actions?
No, it will be clear. I'll give you a group action, and then you just have to solve the. You have to know group actions. If you know group actions, you'll be able to solve almost.
You'll give us the group actions.
We'll see. We'll see. Okay. Let's see. But again, you won't have to come up with a weird group action on your own. Okay. So I mean, there are a few group actions I focused on. Okay, let's do them now. Okay, I will. So orbit stabilizer. I mean, let me say this verbally. Guys, can you hear me like the ones who are attending? What is 7 plus 0, please? What is that? Jeez, it's gonna help. 7. Oh. 7 divided by 0. Thank you so much. Okay. Okay, great. So orbit stabilizer, we all know what the statement is. We all know what a group action is. We all know what a group action is. Should be able to know the definition of it. I won't write this because I want to go a bit faster. We all know what a group action is. Definitions, we all know that. Yeah, you should know the definition. Show something is a group action. If I give you a star, for example, I will show that star is a group action. You should be able to show it. And what as well? Yeah. So this is the basic things. Now, orbit stabilizer. I won't ask you to prove the orbit stabilizer, but it's better to know the details of the proof. That you should, first of all, you should be able to define stabilizer. You should be able to define orbit. You should be able to show that stabilizer is a subgroup. Okay. Now, if I ask you to show something is a subgroup, you can do it by expressing it as a stabilizer of a point. Okay, I can give an example with the normalizer. We did this with the normalizer, if you remember that. We can do this again. Many important actions. These I'll write down again. Action by on the cosets, action by conjugation on itself, action by conjugation on normal subgroups, and consequences on p groups. Okay, these are very important. So if G is a p group, then ZG is bigger than 1, has size bigger than 1, right? We proved that. Then the Sylow theorems also. Okay, so basically orbit stabilizer, you don't need to know the proof, but you need to know the details of the proof. Like, you don't need, I won't ask you to prove it. I won't ask you to prove the orbit stabilizer theorem. But what you should know is that 2 orbits are equal or disjoint. That the orbit partition the set S, right? Being in the same orbit is it's an equivalence relation. Very good. An action is transitive if and only if there is only one orbit. Very good. What as well? These are the basic definitions. And then the main point is that G modulo the stabilizer of S is in bijection with orbit of S, right? Should I write this out? So G mod stab S. Where's the thing? G is a G set. G acts on S, for example, or G is a G set. S is a G set. And S is an S. Be able to define stab S, a subgroup of G, an orbit of S, which is a subset of S. And then you have a bijection between G mod stab S, the coset of stab S, left coset of stab S, and what as well? An orbit of S. And here you send a coset G stab S to G star S. Right? This is the bijection. Right? For those who studied it, this is the bijection. Yeah. I won't ask you show it's a well-defined bijection, show it's surject. I won't ask you that. But you should know it that this is a bijection. This is that bijection. Yep.
But it's just, for example, like when you ask questions like, S is a G set.
Yeah.
And like show it in G says like, yeah, but like, I just don't know how to start, like, how do I define like how G is acting on S?
Yeah, there are few actions that we have seen, right?
Like,
Depends on the question. Depends on the question. Depends on the question it's asking. Okay. Yeah. Yeah, so orb S is a subset of S. Right? And stab S is a subgroup of G. Okay. For each action, yeah. So if G acts on G by conjugation, orbit of S, so your S is G in that case. Orbit of S is the conjugacy class of S. Centralizer of S is the centralizer of S. Exactly, definitely. Okay, so this is the very important point, and then the consequences that if G, so if G is finite, then the size of an orbit must divide the size of G, for example. Okay. Great, and consequences. Okay, is that clear for the orbit stabilizer? Is that like you don't have to know the proof of it. I won't ask you for the proof of that. Okay, for the orbit stabilizer, but I can ask you for example, I can give you a stabilizer, and I can give you the orbit of an action, and I can tell you find a bijection from G mod step S to the orbit of S. For example, I can give you an example. Okay, so if I tell you find a bijection from G modulo the centralizer of X to the conjugacy class of X. So you send a coset of Cx to Gx G inverse. Okay, is that clear? Should I write this down or so? Yeah, I'll write this down first. Just write some examples. I mean, we have many examples. So if S is a set, sim S acts in S, right? You take sigma in sim S and S in S. You send it sigma star S. It's defined to be sigma S. Here sigma is in sim S. And S is in, so the symmetric group on S acts on S, of course, the group of bijection. What do we have? G, H is a subgroup of G. Then G acts on G mod H. How do you define this? So you take G star XH. What is that? How do you define this? Yeah, G XH. This is a transitive action. At least convince yourself if S is finite, this is a transitive action. Okay? I mean, it's always, it's make a choice like that, but we'll just work with minutes. Okay? H is in G. G acts on G mod H transitively. What is what? G acts on G by conjugation. So you take G in G and you take X in G. How do you define G star? It's G and GX G inverse. This is in G. This is in the group G. This is in the set G. Okay, this is an action by conjugation. To justify this in action, I can ask you, show that G acts on G by conjugation. Now, what is the set of fixed point of this action? The orbits of size 1. I heard someone say it. Said it? No? What is the set of fixed point of this action, for example? What are the orbits of size 1 in that case? When is Gx G inverse equal to X? If and only if G for all G and G, if and only if X belongs to. Oops. Yeah, what is the set of fixed point of this action? These are the center of G, right? Yes or no? You remember that?
It's got a name, doesn't it? It's like the set of fixed points is something. It is something.
No,
So
no, it's not a stabilizer. No.
set of fixed points is something.
What do you mean it's something? It's the set of orbits of size 1. Did I? Yeah, did I call it this way? I don't know. Orbits of size 1 and fixed points are the same, right? Yeah. Yeah. Yeah, here at G, the group acts on the set G by conjugation. Here set. Now, of course, the operation is happening in the group, so you're really using that the set is a group, as the group itself. And what is the set of orbits of size 1? So X is a fixed point. X is a fixed point of this action of star if and only if Gx G inverse is equal to X for all G and G, if and only if Gx is equal to Xg for all G and G, if and only if X belongs to Zg, right? So what is the set of orbits of size 1 in this? This is just the center, right? Yeah? Take an element in the center and write down Gx G inverse. The element in the center will commute with everything. So you can write as X G G inverse, which is X. Okay, so you should know this. And what as well, okay? We give one more example like that. We give one more example. So these are important actions, okay? We have 5, 6 actions, well, I don't know, 4 or 5, I don't know how many, anyways. We have few actions that are important. We should know these, okay? And you should be able to come up with them if you need them. Or I can give them to you. I can tell you, let G act on G by conjugation, for example. Yeah. No, conjugacy class is the orbit. What's the conjugacy class of X? Conjugacy class of X is the orbit of X under this action. Right? This is the set Gx G inverse as G is in G. So you hit all the G's. So you hit the X by all the possible G's. Now, when is the conjugacy class of X has size 1? Exactly when X is the center. If this set is equal to X, if whatever G you hit X with, you still get X, then X is in ZG. Okay? So if X is in the center, what's the conjugacy class of X? What's the orbit of X? If X is in ZG, what's Gx G inverse for any G? X, right? So if X is in the center, then the conjugacy class of X is X. And conversely, if the conjugacy class of X is X, then X is in the center. Okay? Yeah, is that clear? What's the conjugacy class? What's the orbit of X? This is just Gx G inverse as G is in G, right? Now, suppose this has size 1. This means that this is equal to X, because X belongs to the orbit. For any G in G, this means that X will commute with any G in G. Okay, great. And what is the stabilizer of X? Stab X is just G in G. So the G star X is equal to X. G in G, so the Gx G inverse is equal to G to X, sorry. Which means that this is just the centralizer of X. I call it Cx, although it's not the standard notation. And then you have a bijection from G mod Cx to the conjugacy class of X. That sends a cosine Gcx to Gx. This is a well-defined bijection. For example, I can tell you, find me a well-defined bijection from these. You also have to know what are the conjugacy classes of Sn, for example. Find the conjugacy class of Sn. You look at the cycle structure two permutation in S5 are conjugate if and only in Sn, sorry, are conjugate if and only if they have the same cycle structures. Now you look at the conjugates class of D4. I mean, we didn't do anything but D4 really. D4, right? We did the conjugates class of D4 many times in homework, so you should know these examples. These are very good examples that I can ask you. Yeah.
Got a whole list of different permutations we did. Remember that before thing where you were sprite? It was like last review session.
I don't know. I can't remember.
Yeah, you right. Remember so many. But I don't see any 1, 2, 3, 4.
Oh, that's the symmetries of D4. That's writing down the symmetries. But I'm saying like the conjugacy classes of D4. Okay. The conjugacy class of D4. You had this in homework 9, right? Yeah. Question 2, I think. Is it? Oh, yes. You have one element, the identity, R squared alone, and then all the sizes are 2, 2. That's right. Yeah, that's right. Yeah. That's right. Yeah.
But to be a group action, all you need is like identity and associativity, right?
What do you mean associativity? Associativity of what?
It's like G1 brackets G2 star whatever X.
So G1 star or G2?
Yeah.
Exactly. Yeah, exactly. It's respect the group operation.
Under
Yeah.
this.
Exactly. Okay. So any question on that? Okay, I'll do one more. I think we can finish the group action part. Okay, we can finish the group action part. Okay, I mean we can do one more, and conjugacy class of X, GCX. This is, for example, I can ask you find the bijection here. You just have to write it down. Okay, great. Now, what's another one? What's another one that you have seen? If H is normal in G, or G acts on H by conjugation. Okay, this is homework. We did this in the homework, right? And what is the set of fixed point of this one? What is the set of fixed points? H intersection ZG, right? We did this in a review session before, no? So and set of fixed points. Do you mind if I stay a bit more than that? I just want to give you everything you need to do. You need to know for all the main theorems. Set of fixed points is H intersection ZG. Do you want me to rederive this or no? Do you want me to do this again? I can do that again. So I've done it like, but that's okay. That's it. It's the same as this. So first of all, so let G be in G and X be in H. I define G star X. What do I define it to be? By conjugation, what do I define this to be? Yeah, very good. This is conjugation. Now there's something I need to justify. Why does Gx G inverse belong to H? What am I using here? Subgroup H is normal. H is normal. So G X G inverse belongs to H. Any questions from the people attending? Okay, guys, is this clear? Do you want me to show it's a group action as well? Do you want me to do the whole thing? Do you want me to do it or is it clear? This one, it's a group action. Is it clear it's a group action or should I do it? Don't hesitate to say if you want to do it. Pardon me? No, I mean it should be for, I don't know. Well, I mean, I don't know. Any of these questions we're gonna find out there.
Or like verbally, like quickly, just like.
Yeah. So just as show that the axioms hold.
I didn't see any associativity the thing.
Exactly. So exactly. So E G star X. What is that? This is X. Do you want me to? I could write this. That's okay. Okay. So E G star X. I mean, it's the same proof as here, right? As just like the. EG star x, what is that? Let x be an x, let x be an a. EG star x is just EG x, EG inverse x. G1 star G2 star x, what is that? G1, G2, G. What is this one? Talk, talk, talk. This is just G1 star G2x inverse, which is just G1 G2x G2 inverse. G1 inverse. This is one G1 G2 x G2 inverse. G1 inverse. This is the same as the regular one. Okay, so this is a group action. Now, what is the set of fixed point of this one? There you go. Same proof works. Here we just say x is an h. Is a fixed point of star if and only if all of this holds, right? The same proof works here. Right? X is an h is a fixed point of star if and only if gx g inverse is equal to x for all g and g and so on. So x is an h is a fixed point if and only if x belongs to zg. What is the set of fixed points here? Yeah, right? Set of fixed points. What is the set of fixed points in that case? X is a fixed point if and only if x belongs to zg. What is the set of fixed points? X is an h is a fixed point if and only if x belongs to zg. So the set of fixed points is h intersection zg.
How is this different than the one before?
How is this?
Like different than the one before?
Oh, the one before is that you're taking x is g, h is g, sorry. Because g is normal in g. Here you're just making it a bit more general.
Okay.
H is a normal subgroup. So what is that? Set of fixed points. Is h intersection z. Right? Now, if you let h be is g, what is g intersection zg? This is zg, right? Very good. Okay, now you have one more action. These are the ones that we have seen, and there are a bit more, but I think these are the main ones. That doesn't mean that I won't ask you more, but these are the main ones. So 5. If H is a subgroup of G, G acts on the set X, H, inverse at X and G, right? On the set of conjugates of H. You take G star X, H, X inverse, what do you get? You get G. Right? This action is transitive. This is transitive action. According to us, the transitive action. What is the stabilizer of H? Stamp H. It's just G and G, which on GH, G inverse is equal to H. What is that equal to? What do you define this? What is this called? What do you call this? Normalizer. Normalizer of E of H. Okay. Remember that? So if I ask you show me the normalizer of H, well, I mean, you know. Yeah, anyways. This is normalizer of H. Are we good here? This is stabilizer of H. What's the stabilizer of the element H of S here? H is an element on which G acts. What's the stabilizer of H? This is just a set G and G. So that G star H is equal to H.
But where did the X go?
H. One is X, H, X inverse is equal to H. Put X equal 1. Is that clear? Yeah. You can put X any H and H. You also get H. You agree that H is an element of this set. If H is an element of this set, then you can consider it a stabilizer. Okay?
So H is just any element.
It's not any element, it's one element. H belongs to the set. Let's call this S. H belongs to S. Is H conjugate to itself? Because H is one, H one inverse. So H belongs to the set. Okay? Great. Great. Good. Okay, now you have the restriction of the action of G on S. If G acts on S, also there most things in Sylow theorems. If G acts on S, then and H is a subgroup of G, and H acts on S as well. Okay, this is like kind of 6. Okay, great. Awesome. Now we move on to P groups. P groups. Now the most important theorem of P groups, what is that? If G is a what is the definition of P group? G is a P group. Finite. P is a G. It's P to the K. Of course, P is a prime. P prime number. J is P to the K for some K and N. Agree or not? This is the definition. Well, I mean, you know, we're going to consider it to be the definition of P group. Then, that. The very important theorem, you should know how to prove it and to use it. G is a P group if G is a P group. P, when I say P group, P is prime always. G is a P group. And S is finite G set. And the size of S is congruent to what? To the number of fixed points. Mod P. And this is proved by the orbit stabilizer. You're responsible to prove that and to use it. Why don't we write stab? Can you possibly show us how you? Yeah, sure. I will do that. I will just do that. Why don't you write stab x h x inverse? You could write that. Yeah, you could write that. But it will just be what is stab x h x inverse? So some ask that question. This will just be x stab h x inverse. Yeah. And it will just be x indicated x inverse. Here I'm using a result that you proved at homework needs. Okay. Great. So it's number of fixed points mod P. You should know how to prove it and to use it. Prove and use. I mean, let's use it. Example. So let G be a group. Let G be a P group. So that G has an element of order P. Okay, let's prove this. Very quick proof. That could be that easily could be a question. You could have something like that. Let G be a P group, show that ZG contains an element of order. So first, G acts on G by conjugation. Where's finite? Finite P groups. What is the set of fixed points of this action? What is the set of fixed points of G acting on G by conjugation? Everybody, what is the set of fixed points of this action? 2 pages before. For all G and G, this means that ZG, if and only if X belongs to ZG, right? Set of fixed points says that X points is ZG. Hence, what is my G set here? G is acting on S, right? So what is my S here? S is G. Hence G is congruent. The number of fixed points, what is the number of fixed points here? Is the size of ZG, right? Mod P. Now G is G congruent. What is G is a P group. So what is the size of G mod P? P to the K mod P is equal to K is bigger than 1, bigger or equal to 1. So K P to the K mod P is 0, right? 0 is congruent to ZG mod P. Yeah.
Do we need to know how to prove?
Yes. Yeah, definitely. Proof. I did it the day after. Okay, the day after I did it. The day after I did it, I think. Is that right?
Yeah.
ZG is congruent to 0 mod P. That's one way of doing it. And then what can I say? Can ZG be 0? Definitely not. So ZG is either P, P squared, or P to the K, right? So ZG has size divisible by P. So ZG is a subgroup of G of size divisible by P. What theorem can I conclude here? What theorem can I use to show that G has an element of order P if P is a prime and G has size divisible by P? Cauchy's theorem, right? Cauchy's theorem. G has an element of order P. Okay? Very, very, very good questions. These are very good questions like that. You can easily have a question like this. This could easily be a question.
Do you want to prove that G has an element of order P?
ZG. Thank you. Of course, G has an element of order, but that's you don't need that. Okay? Great. Now here, property of P groups as well. All of these you have to know. Again, it should not, if you study the homework, if you did the homework, if you spend time on the homework, it should not take you a long time. People attending online, do you guys have questions? People here have questions? Yeah. You have a question? Oh, okay.
So what did you say we have to learn? Just now?
No, I said like if you did the homework and if you did everything, it should not take you a very long time. Okay.
The exam.
No, this one.
Oh.
And the exam either. The exam is not. If you know how to do every question, it should be pretty quick. Okay, and you will see a lot of questions you have seen. You will see that. You will see that you have seen a lot of questions. Okay, so I'm not great. So what as well for P groups? Okay, so the converse of Lagrange's theorem for P groups. I proved it in class, right? I proved it by induction. You remember this proof? This is a bad proof. It's a bad one. You should know the result and know how to prove it.
Oh, so we should revise induction because I was planning on that.
No, I mean it's an obvious induction. I won't ask you like prove that 1 + 2 + n is n times n + 1 over 2. I won't ask you that.
Like an applied induction.
Yeah, I mean when you need it for groups, then yeah. But I won't ask you like prove that the sum of 1 squared plus 2 squared plus n squared is equal to 5 over 1. This one. Now you want a question like that? I'll edit it there. I'll add one more then. I'll put on 1 point,
Bonus.
bonus. Okay, no, I mean yeah. In analysis, do you do induction? You have like questions on induction? Oh, in Comp 250. Okay. In analysis, you have induction questions. Like hard induction question or just something like that. 1 plus 2 plus n or something. Like a statement about natural numbers. It's not like a proof. It's not an actual proof. It's not like applied to prime numbers. It's like a proof on, I don't know, something is divisible by 6. Something that depends on n. Okay. Yeah. So in this course, we'll leave it for analysis. Here we will do induction as groups. We will do induction as groups. Here we do it by induction. Have you seen this proof? The people who study P groups, have you seen this proof or not? Yeah, it's an annoying one, but it's not bad. It's not bad. It's like a few lines, and then it's an induction, right? You take an element x, right? You use this one here. You take an element x of order P and ZG. Take the subgroup generated by x. You show it's a normal subgroup. You quotient G by this subgroup. You can apply the reduction hypothesis here, and boom, right? This is how you do it, no? Yeah. Anyways, you should know this proof. Now, more importantly, Sylow theorems. Sylow theorems. What are the 3 Sylow theorems? Statement of the 3. And proof of second and third theorems. Okay, you should know the proof of that. Those are P groups acting on sets, right? Why is the cardinality of G equal to the cardinality of Z given P? Yeah, because if G is a P group and S is a finite G set, then the size of S is congruent to the number of fixed points. Okay? Now the G set here is G, right? The G set here is G. So the cardinality of G is congruent to the number of fixed points. Now the number of fixed points happen just to be the cardinality of ZG because ZG is the size of fixed points. Is that good? Yeah. Okay. We'll finish. We'll finish this. We're just gonna tell you. I mean, yeah, it's a 3-hour exam and the topics are taking 2 hours. Anyways.
Yeah, was that?
I'm giving the details, right? I'm giving the more details.
Was it the statement of first?
Second and third theorem. Sylow theorem. Third Sylow theorem. So
The
one
one, the one
No,
about
the one above.
statement of the.
3 theorems. There are 3 theorems.
Is algebra 1 now? Is it much easier than it was when Newton?
I don't know. I just let's not compare. Listen. Okay. Are we good here? Great. Now the last part. This is the most important part. What is it? Coset representations, group actions, and homomorphisms. Okay, so let's get okay, great. Coset representations and group homomorphisms. Of course, you have to do the proof of Cayley's theorem. Let me just write them down here. Cayley's theorem and applications. Or one more thing on P groups. 6, is it 6? What is that? 5. So now it's 6 or it's 5?
No.
5. Okay. Any group of order P squared is a billion. Now for that, you need 2 things. That you need that ZG is bigger than 1 if G is a P group. And you need the fact that ZG cannot have prime index P, right? You've seen in the homework, if G mod ZG is cyclic, then G is a billion. You remember this? Yeah. Okay, it's a lot. I agree, it's a lot. But sorry. Okay, so things like that. Homework, what is it? Homework 6, for example, homework 6 are important. It's important in this case. In all the homework 6, 7, 8, 9. How do I write this? Let me write this in a very. Let me write this here. This is more important. Okay. This is less important. Okay. This is less important. 7, 8, 9 the most important. 6 is less important. Right. Great. Now the most important is coset representations and group actions on sets and homomorphisms induced. So the first proof is Cayley's theorem. Cayley's theorem. Proof and result. And you should be able to state it and prove it. Plus applications. In homework 7, we've seen an application. Remember this? We've seen an application in homework 7. Third theorem, really long proof to be put on the final. Yes, so the third theorem is long, but the way I could do it is I can tell you that assume that P acts on the set immediately, right? Right, I could tell you what to assume. Or I can tell you in a previous question, show that G acts on the conjugates and then restrict it to the Sylow P subgroup. Okay. The third theorem is a bit long. I can still ask you parts of it. For example, show that if P is a Sylow P subgroup of G, then P is a Sylow P subgroup of NG, for example, things like that. Okay. I could ask you parts of it, or I can ask you the entire thing. Okay, great. Now, if G acts on S, yeah, homomorphism is one of the most important parts from G to sim S. What is the kernel of this homomorphism? Homomorphism rho. So rho from G to sim S. It sends G to lambda G, where lambda G S is G star S. So you have proof plus statement. You have to know the statement. You have to know the homomorphism. What is the kernel of this homomorphism? Is the intersection of all the stabilizers, right? Okay. Yeah. Any questions? 5 more minutes and we end this. 10 more minutes and we end this. Okay. Let's see. I mean, I'm just giving them a bit more in details, right? I'm not just telling you this and this. Okay. Yeah. Yeah. You prove that. And then the most important part is like coset representations. So G acts on G mod H. If H is in G. Right. Now if H has index n, then the kernel of rho is the intersection and then G of XH X inverse, which is a subgroup of H, and G mod rho is isomorphic to a subgroup of Sn. We call this the coset representations. Coset representation. We've done many applications on this. Okay, how many applications did we do on that? Do you remember or not? but quite a bit, quite many applications. Okay, so see all the applications. Like, please do all the applications one by one. Okay, one by one. In the practice final that I'm preparing, I'll release it on the Wednesday. You'll see that there's be a lot of focus on this. And it's going to be a lot of them is going to be like the homework. Okay, you just have to think a bit how to apply them. So see homework 8, 9 plus lecture notes. What is homework 8, 9 plus lecture notes plus exercise session. In one exercise session, we did a nice co-set representations. So remember one good example that we can construct a surjective group homomorphism from S4 to S3, showing by using the action of S4 on the cosets of S4 modulo H, where H is a subgroup of order 8. How do I construct a subgroup of order 8 in S4? E4, exactly, right? If I tell you write down a subgroup of order 8 in S4, how do you do that? What do you do? The battery is over. But okay, so we can do. Do you want me to go through this example again or not? Surjective map from S4 to S3. Do you know how to find that? We did this many times. Should I go through it again? I could do that.
Verbally.
Pardon me?
Verbally.
Yeah, sure. So you have a subgroup H of order 8 in S4. What is it? What is one possible? You take the symmetry of the square, you label your square 1, 2, 3, 4, and you write down its symmetries: vertical, horizontal, diagonal, and the 4 rotations. You get a subgroup of order 8. You consider this, is this subgroup normal or not? No, it's not normal. You can prove it by many ways, but one way is to conjugate it by something that is not in it. And you lie outside. Great. You conjugate one element of that by something that is not in it, and then you will lie outside this subgroup. Then you take the action of G on the set of cosets of this subgroup. Then you get a homomorphism from this coset. This subgroup has index 24 divided by 8. So what is the index? 3. So you get a homomorphism from S4 to S3. Great. Now you look at the kernel. The kernel is not 8 because the kernel is contained in that H, but H is not normal. So if you look at the first isomorphism here, G modulo kernel must divide 6 and must be strictly bigger than 3. So G mod the kernel must have size 6. This means that the kernel has size 4. Now, how many subgroups of order 4 do I have in, how many normal subgroups of order 4 do I have in S4? Only 1, which is the 3 2x2 cycles and the identity. You're going to write this down or it's fine? Okay. We've done this in the homework, like this question's appeared in the homework like 2 or 3 times, and we did it in class 2 times in different way. Okay, so please know this. Okay, it's an important question, and it's a nice calculation question. And how many subgroups of order 8 can you find in S4? 3, exactly. You remember this? Okay, great. So let's call it a day. Unless you want me to write it down, I could write it down. If anybody in the audience wants me in the online wants me to write this down, I can do that. But if not, you can just call it a day. If you guys have questions, I can answer them.
So
Yeah, just not. Yes. Okay, so please study this. It's easier said than done, but okay, so it's I hope this was helpful. At least it reduced the amount of stuff you have to know. Not by much. Pardon me? Yeah, I mean it's reduced by a bit, but again, these are the proofs you should know. Okay, so again, I eliminate the orbit stabilizer. I made the first isomorphism. So this P group business, the converse of Lagrange, throw it away if you want. Okay. So the converse of Lagrange for P groups, throw it away if you want. Don't study it. I won't ask you on that. Okay. That's one less. Yeah. The proof, not the statement. The statement you should know.
So the long one.
Don't worry about it. Okay. Yeah, the induction one's don't worry about it. It's yeah, I mean don't it's yeah, I'll send it right here. It's a no. I mean, it's a bad proof. I don't like. I mean, because you have to assume many things, right? So it's a that's one less. Okay, but any cute proof, you know, a few lines, it could be there. Okay, any cute exercise could be there. Okay, right. So I'll post today. I'll post like some review problems on roots and try them all. You will see that they will be a bit harder than the ones on the final. So just you know to prepare you better, they should be fairly accessible to you guys. Okay, they should be fairly accessible. Some of them are really hard, so I don't expect you to do them. I mean, you will see if they're really hard.
You like write down.
Yes, I will write down hints. When you see like 5 hints, it means it's a bit
Okay.
tough. But again, with the hints, go one after the other. If you cannot manage to prove it, use what you like. Use the hints, okay, and then you can prove it easily. Okay, great. Any questions from the people attending?
Assignment grade, you go over 100.
So for the assignment grade, so it's on 400s, right? The ones that are due, it's on 400. So on these ones, no, I will take it on 350 and I will cap it. But you have the bonus one that I will add on 350. So do you want me to explain how I look at it? So I have 400. All except the bonus. That I will take the max of your grade and 350.
They combine together.
Exactly, combined together,
Okay.
except the bonus. This doesn't put the bonus. All your homeworks are worth 400, right?
It's not like taking away like the stuff.
No. It's even better. It's a better
Okay.
deal for you. Right? You realize that.
Yeah.
So I take max over here and I put on 350. Okay, now your grade on the bonus is on 40. So I will add plus bonus on 350, even if you exceed. That's fine. Okay. Yeah. No. Even if it exceeds, it doesn't matter. Whether it's for the homework or not. So let's say if you have 400 here, so put it 400 on 400. Okay, 400. 350 max 400. 350. Sorry, min. Sorry, min. Yeah, not max. Min 400, 350. Okay, min 400, 350 over 350. And say on the bonus you get 30 on 40. So you get 380 on 350. The homework are worth how much? 25? 25? So you get 38 on 35 times 25. 38, what's that? 5 divided by 7. 125. Okay, so you can exceed more, but only by the bonus. Everything that is due, you cannot exceed. I will cap it. Okay, and then the bonus I won't grade until the end. So I will see if I need to grade it for you, I will grade it. If I don't need, no, I mean I'll release the solutions. So yeah, but I mean it's I have to grade it, so it's 200. Yeah. Okay. But again, many will be graded based on completion, so it's not. Okay. Any people? Anyone attending online has questions? I can ask them. No, if you submit a blank page, then no. No. If you submit a blank page, then no. I mean, I graded some of them. Some are blank. I didn't award marks. Submit something, yeah, and something relevant. It's not like, yeah, something relevant. You know. Any questions? Okay, great. So let's. But I mean, not all of it will be graded on completion. Maybe like 5 marks on 40 will be on completion. So it's not a lot. It's gonna be on completion. It's really not a lot that is on completion. So it's and then many of them have been done in class really. So like Yeah. So I mean, for this stuff, everything over 8, 7, and 7 here. So 7, 8, 9 plus lecture. Okay. People attending online, any questions or no? No problem. Okay. Great. If you guys have questions and I could answer them, I'm sure that all your questions are all good. Okay, great. So I should end this. So if you have a question, please ask before. Bye bye. See you. If you have a question, please ask before I shut this. Okay, so people are. Questions? No more? Great. No questions, everyone? Okay, great. So I will just end this. If anyone has a question, please last call for questions before I end this. Give it 1 more minute. Okay. It's 10 more seconds. Okay, see you all. Bye bye.